Okay, in the last video segment, we were looking at the differential mode gain of our 9-transistor current mirror diff amp, and we found that ADM was given by, with the load capacitance that is, was given by GM1 times RO4 parallel RO8 divided by 1 plus j omega RO4 parallel RO8 times C out. And we can define some things here. We could take this and define this as a time constant tau. It's an RC product. And we could take this thing here and define this as a low frequency gain, which we're going to denote A0. Okay. So what we'd like to do is sketch this in a Bode plot. So this is going to be A0 divided by 1 plus tau s. And so just to remind you what a Bode plot looks like, we have two plots that we make. One is the magnitude. So it's the magnitude of ADM. It's expressed in decibels typically, versus omega, and this is on a log scale. And then the other thing that we plot is the phase angle, which we might denote angle of ADM, and that's typically plotted in degrees. Sometimes it's plotted in radians, but we'll plot it in degrees, versus omega, and again this is a log scale. And these horizontal axes are aligned. And so we have here a gain that's positive, okay. GM1 times RO4 parallel RO8 is a number that's like on the order of like 100, somewhere between 100 and 1,000 maybe in moderate inversion. On the bias current, maybe it's going to be on the order of like 60 or 80 with strong inversion biases. But it's going to be a number that's bigger than 1. And so when you express that in dBs, which is 20 log to the base 10 of whatever that number is, so a gain of like 100 would be 40 dBs. 20 times the log to the base 10 of 100 is 20 times 2, or 40. So that'll be up here somewhere. So if this is the 0 dB line, and this is the 0 degree line, it might be somewhere up here. And if we're considering tau to be sort of a relevant quantity here, on a frequency scale we might want to denote 1 over tau as a special frequency of interest. Okay, and so for omega much less than 1 over tau, we can look at the behavior of ADM. So for, I'm sorry, this shouldn't be S, this should be j omega tau. So for omega much less than 1 over tau, we can write ADM as approximately being A0 divided by 1 plus something that's small compared to 1 in magnitude. So it would be like A0 over 1 plus small, which is just A0 over 1 plus, A0 over 1. And so this is just A0. So the magnitude is A0, and the phase angle is going to be 0. And so if we're in this region here, we're in this region here, and this region here. So if we look at omega tau, or omega much greater than 1 over tau, this would be somewhere over here. ADM is going to be, well, if omega is much bigger than 1 over tau, then it's the imaginary term that's going to dominate down in the denominator. And so ADM is going to be approximately A0 over j omega tau, which is, if we rationalize the denominator, it's going to be j over j. We can write this as minus from the j squared downstairs, A0 over omega tau times j. So here j is the square root of minus 1. And so we have that the magnitude is going to be falling off inversely with frequency. So it falls off as 1 over frequency. And it's going to be, that means that on a dB scale, every factor of 10 we increase in frequency, we're going to wind up decreasing the magnitude by an order of magnitude, and that'll be a minus 20 dB change in magnitude. So we're going to go down on a slope of minus 20 dB per decade increase in frequency. And the phase angle, since this is an imaginary number with a minus sign, is going to have to be minus 90 degrees. So if you imagine the complex plane, where this is the imaginary axis and the real axis, something like minus j is down here, and so it's going to be an angle of minus 90 degrees with respect to the real, positive real axis. And so we've got here minus 90. And so well above the corner, or well above this frequency 1 over tau, we're going to be on a slope of minus 20 dBs per decade. And we're going to be approaching minus 90 degrees. And so for omega tau equals 1, or omega equals 1 over tau, this is just at this frequency right here, ADM is exactly equal to A0 divided by 1 plus j. So the omega tau is just 1 at this frequency. And if we like, we can, again, well, we can write the magnitude. We can write these two numbers in polar form, if we like, as the magnitude of A0 times e to the j0 divided by, well, 1 plus j is, so this is the imaginary axis, and this is the real axis, 1 plus j so this is magnitude of root 2, an angle of 45 degrees. And so I don't want to write this. All right, I'm going to write this using a different notation here. I'm going to write this using what's typically called Phasor notation, where we have the magnitude of A0, angle 0, and the magnitude of the denominator is root 2, angle 45. So this just means root 2 times e to the j times whatever pi over 4. And this is the magnitude of a0 times e to the j 0. And so when you take the ratio of two numbers in polar form, two complex numbers in polar form, we can write this as the ratio of the magnitude, so it's 1 over root 2 with an angle of 0 minus 45, like so. And so a0 divided by root 2, if we convert that to dBs, we get whatever the magnitude of a0 was, which is denoted here in dBs. And then because we have the log of a ratio is the difference of the logs, we have basically whatever the root 2, we're down by whatever root 2 is in dBs. And it turns out that root 2 is very close to minus 3 dBs. And so, as it turns out, these straight lines kind of meet at this frequency, which is called the corner frequency. But the actual magnitude is down by 3 decibels. So the curve goes something like this, and this is 3 decibels. The difference between the curve at the corner and the place where those asymptotes intersect. And then the actual curve is halfway between the 0 and the minus 90 at minus 45. And basically what happens is that this change in magnitude or change in angle starts about a factor of 10 below. So this would be 1 over 10 tau, and it finishes up by about 10 times the corner frequency. And in terms of the magnitude, the magnitude starts deviating significantly from that straight line asymptotic approximation in about an octave, which is a factor of 2 in frequency. So this is about 1 over 2 tau, and this is about 2 over tau. This is A0 in dBs, and this is what the gain of the circuit looks like on a Bode plot. It's a typical first order low pass kind of response, shifted up by whatever the low frequency gain is, in this case maybe in the range of 40 or 50 dBs being typical. Okay, so that was kind of the Bode plot representation of the gain that we found for the differential mode operation of our 9-transistor diff amp. And what I wanted to do with a capacitor on the output, what I wanted to do next is to consider a similar calculation, only with unity gain feedback around our amplifier. So we're going to connect it up like you're connecting it up in experiment 3. And so we're going to look at the frequency response of a follower connected current mirror diff amp. And we're going to use node fixing for this again. And so here's our circuit. We've got the diff pair. We've got our current mirrors. Here's our input Vin, bias voltage VB, and this is going to have unity gain feedback, and so we're going to connect the output back to the inverting input, which is V2. And so we're going to have an output capacitance like we do in the lab and like we did last time for the open loop configuration. C out. And we would like to calculate the gain of this circuit by node fixing. And so I'll put in here M1, M2, MB, M3, M6, no, M4 is here, M5, M6, M7, and M8. And so the first thing is to think about where the quiescent output voltage is going to be, because that's where we have to adjust the output voltage source that we're going to attach. Well, this is a follower, and so ideally the output voltage should be whatever the input voltage is. Now in practice there's going to be a bit of an offset between the two, but it's not going to be tremendously huge. It'll be, you know, something like a few millivolts, maybe 20 millivolts at most, typically. But we're going to assume that basically V out under quiescent conditions is the same as V in. And notice that is basically the common mode condition that we were talking about last time, where the two are basically balanced. And so V out is being held fixed at basically V in. And what we're going to do is calculate the transconductance gain of the circuit if we apply a delta V in to our input on top of some DC level. Well, that's going to give rise to a delta I1. I guess I should say we're interested again in the delta I out that flows out of the circuit. That delta I1 gets mirrored by M3, M4, and it all comes out. The same reasons that we talked about last time. The delta I1 flows back around here and flows back up the source of M2 and is mirrored by M5, M6, and then by 7, M7, M8. And so we have another delta I1 that flows out of the circuit as well, bypassing the capacitor because the output is being held fixed. And we have that delta I1, or delta I out, is equal to 2 times delta I1. And just like it was last time, that's going to be GM1 times delta V in divided by 1 plus 1 over GS1 times, GS1 times 1 over GS2. But in this balance condition, GS1 equals GS2. And so this is just two times GM1 over 2 times delta Vn. And so the GM of the circuit as a whole, which is in this case delta I out over delta Vn, is equal to just little GM1, which is exactly what we found last time. Okay, so now we move on to the second part of the calculation. Once we remove these little pesky current arrows. And we're interested here in looking back into the output of the circuit. We're going to increase V out by some delta V out. In this case, it's going to be a sinusoidal excitation on top of the DC level, the quiescent DC level, at some driving frequency, because we have a capacitor in the circuit. And like last time, we're going to actually put in the early effect resistors on M4 and M8. And we're going to apply source splitting and superposition to figure out what is the R out, which is going to be the ratio of delta I, or delta V out to delta I out flowing back into the circuit. And so in this case, we're going to actually have 6 things that are connected here. We've got the 4 from the drains of the 2 output transistors and their respective early voltage resistors. We've got the capacitor, and we've got the gate of M2. Okay, so we are going to split this into six replica sources, and consider the 36 possible components. Yikes. Of delta I out. Here's hoping that matrix is sparse, as advertised. Okay, so here's number 1. Number 2. Three. 4. 5, and we lost the capacitor here. 6. And we're interested in the total amount of current flowing through this bundle, giant bundle of 6 wires. And so we're going to, instead of applying all of our output sources simultaneously, we're going to apply them one at a time and accumulate our delta I out, and they combine by superposition. So let's start out with our delta V out here on branch 1. What are we talking to here? Well, we have an early effect resistor, and we're going to have a delta I out 1, 1. And that is going to be simple enough. It's going to be given by delta V out over RO4, which is incremental Ohm's law. And that's delta I out 1, 1. And notice that that flows directly back to the power supply. It doesn't affect the voltage on the power supply at all to absorb that little bit of change in current, and so it has no other effect anywhere in the circuit. It doesn't flow back the source of M4, it just flows back to the power supply, and that's all it does. So of the 6 possible components due to delta I1 or delta V out on branch 1, we get just one non-zero component. So move on to number 2. Delta V out on branch 2. We're talking to the drain of M4. It's an ideal saturated transistor. We're encapsulating the early effect on that transistor in RO4 anyway. And so if we change the current or change the voltage on branch 2, we don't get any change in the current in the transistor. and we're not changing anything else anywhere else, and so there are no components of I out or delta I out due to the delta V out on branch 2. So we now have 12 of 36 components been considered, and we have one non-zero component. All right, so let us skip over number 3 for the time being, and let's move on to branch 4. Well, branch 4, what's that connected to? That's the drain of M8. Well, again, that's the drain of an ideal transistor. In this case, it's an NMOS transistor that's operating in saturation. We're encapsulating M8's early effect in RO8, and so there will be no current flow in branch 4 due to that change in voltage, and there's nothing else changing in the circuit. So again, we have 6 zero components due to delta V out on branch 4. So we've considered 18, which is half of the 36 possible components, and only one non-zero component so far. Move on to branch 5, delta V out. Well, here we're talking to an early effect resistor, and we have a delta I out 5.5. And that's going to be given again by incremental Ohm's law. So we have a delta V out over RO8. This is delta I out 5.5. Again, that flows on the other side to ground and doesn't elicit any other change in currents in any other branch. So now we've considered 4 of the 6 branches, which is 24 of the possible 36 components, and only 2 have been non-zero. And now we move on to branch 6, put our delta V out here. And now we're talking to a capacitor. And so there's going to be a current flow in the capacitor, delta I out 6.6, which is going to be given by delta V out over the impedance of the capacitor, which is 1 over j omega c. And so that's going to be delta V out over 1 over j omega c out. This is delta I out 6.6. But that branch is completely isolated from the rest of the circuit, and so there's no other of the 5 possible components that we could have due to that that are going to be non-zero. So now we've considered 30 of the 36 components of delta I out, and only 3 have been non-zero. Now let's go back to branch 3, which is kind of the new one that's caused by this feedback connection that we've made. And here you'll notice something very interesting. This is actually just like the situation where we were changing M1, only now we're changing the gate of M2. So back in the GM calculation, we put a delta V in here, but now we're putting a delta V out on the other side. And so what we get as a result of that delta V out is actually going to be quite similar to what we got for the GM calculation. Okay, only now we split the source, and the two sort of different effects as we go around different pathways in the circuit are going to come out in different branches. Okay, so we're increasing the current in M2. So there's a delta I2. Okay, and that's going to do 2 things. It's going to be mirrored by M5, M6, delta I2. And then it's mirrored by M7, M8, delta I2. And it comes in to the circuit. So it represents positive delta I out, and this is a delta I out in branch 4. due to replica source 3. And so we're going to have delta I2, which is given by GM2 times delta V out over 1 plus GS2 times 1 over GS1, because that is the incremental resistance down here in the source degenerating the source of M2. It's basically the source conductance of M1. And again, we have GS1 equals GS2 under the balance condition, and this whole thing is going to be delta I out in branch 4 due to replica source 2. And so this is just going to be GM2 divided by 1 plus 1, which is half of GM2. Well, the other thing that this delta I2 does is it flows out of the source and back up M1, out the drain of M1, and it's mirrored by M3, M4. And that will represent a delta I out component in branch 2 due to replica source 3. So that's a delta I out 2, 3. And that again is going to have a positive sign because it's being drawn into the circuit, and our delta I out for this R out calculation or Z out calculation is positive flowing in. And so we're going to have again GM2 times delta V out divided by 1 plus GS2 times 1 over GS1, and that again is delta I out in branch 2 due to replica source 3. And again, we're at this balance condition where GS2 and GS1 are the same, and so they cancel, and we have GM2 over 2. Notice that these are both GM2 over 2 times delta V out. So we can combine these two terms, and that'll just be GM2 times delta V out. Okay? And so we can group these things in the following way. We can factor out the delta V out from the first two terms. And we have 1 over RO4 plus 1 over RO8. And then we have a GM2 delta V out, which accounts for the last two terms. So we have this one accounting for the first two terms, this one accounting for the last two terms, and then we've got the capacitor here. So the capacitor will pop up into the numerator, and this becomes J omega C out times delta V out. And this thing here is just 1 over RO4 parallel RO8. And so here we have a situation where we have GM2 times delta V out, and we've got a conductance that's like 1 over the parallel combination of two early effect resistors. And to the extent that our GM1, which is the same as GM2, times RO4 parallel RO8 is a large number, which is our low frequency gain, then the first two terms are going to be dominated by this second term. So these first two terms here are approximately just GM2 times delta V out if GM2 times RO2 parallel RO8, sorry, RO4 much greater than 1. Right, so this basically boils down to GM2 plus j omega C out times delta V out. And so that means that our Z out, which is delta V out or delta I out, is going to be basically given by 1 over GM2 plus j omega C out, which we can, if you like, write in sort of a normalized form. When we have something like this where there's a frequency-dependent admittance, which is the generalization of conductance, like impedance is the generalization of resistance, it's nice if we factor out the real part here and basically normalize that constant coefficient in the polynomial in j omega to unity. So we're going to factor out a GM2, and so this is equal to 1 over GM2 divided by 1 plus j omega C out over GM2. I know our tendency is to not put nested fractions in, or not to like to see nested fractions in here, but C out over GM2 is basically an RC time constant. All right, so this is a tau. And what we want to do is see what the gain of the circuit was. That was our goal initially. So this is Z out. And so the gain, I can hose this stuff down here. A, which is delta V out over delta V in, sorry. Voltage gain is GM times Z out. And that's going to be GM1 from the GM times 1 over GM2 divided by 1 plus j omega C out over GM2. But GM1 equals GM2 because of the balance condition in the diff pair, and so this is just equal to 1 over 1 plus j omega C out over GM2. Okay? So we want to look at this on a Bode plot. One thing that we'll note right away is that if this imaginary part here at low frequencies disappears, the gain is just 1, which is quite comforting because it's supposed to be a unity gain follower. And then there's going to be a corner frequency at 1 over this time constant, so GM2 over C out. That's the angular corner frequency. And that'll be, again, down by 3 decibels, just like it was for the open loop gain. And then when we get above this corner frequency, we're going to be falling off at a rate of 20 dBs per decade. So if we were to sketch that, if A is equal to 1 over 1 plus j omega C out over GM2, magnitude so if we call this over omega 1. Call this omega 1. And we plot the angle. In degrees. We're basically at low frequencies, which are omega for omega much less than omega 1. A is about 1 angle 0. So it's real and it's unity. And for omega much greater than omega 1, A is going to be basically, well, that's going to make this the dominant term. It's going to be the omega 1 is going to pop upstairs, omega 1 over omega j omega, and that's basically omega 1 over omega angle minus 90. For the same reasons that we had, if we rationalize the denominator, we get a minus j, and that's going to be have a magnitude of 1 and an angle of minus 90. And so we're going to have a roll off here of minus 20 dB per decade. And the phase is going to be approaching minus 90. And at the corner for omega equals omega 1, we got A is equal to 1 over 1 plus j, which is equal to 1 over root 2, angle minus 45. And so that's going to be down by 3 dBs. From the intersection of the straight line asymptotes. And again, this is going to be approximately 1 over omega 1 over 10. This is going to be approximately 10 omega 1. Okay, one more thing I want to bring out before I call this one done. If we sketch up our open loop gain here, again, this was ADM in dBs versus omega. We had this A0, and then at this frequency 1 over tau, we started falling off on the same slope of minus 20 dB per decade. We had a similar kind of phase response. In degrees. Minus 90, minus 45, and in this case it was at 1 over tau, so it was shifted. Something like that. If we ask ourselves, what is this frequency right here? Where does this cross the 0 dB line? Well, A0 if you recall A0 was RO4 parallel RO8. GM1 times RO4 parallel RO8. And tau was equal to RO4 parallel RO8 times C out. Well, this line with a slope of minus 20 dB per decade represents a decade change in frequency with every decade change in gain. And so this slope here of minus 20 dB per decade means that for every decade change in gain, we have a decade change in frequency. And so the ratio between the gain here and the gain here is A0 to 1. This is a 0 dB line, this is A0. And so the ratio of the gains between here and the 0 dB line are A0. And that means since these 2 points are on this line of slope minus 20 dB per decade, this frequency should be basically, the ratio of these two frequencies should be the same as the ratio of these two gains, which means that this frequency should be A0 over tau. Okay? Well, what is A0 over tau? We can just divide these two things. All right, so A0 over tau is equal to, well, the RO4 parallel RO8s cancel, and we're left with GM1 over C out. And if you recall that GM1 is the same as GM2, then it turns out that this frequency is the same as omega 1. So when we take our amplifier that has the open loop gain shown in this Bode plot and configure it as a unity gain follower, what we find is that we basically get the corner frequency corresponding to the place where the open loop gain crosses over the 0 dB line. So the unity gain crossover frequency is what that's typically called in the open loop response. And that's typically denoted by omega 1. Okay, so just wanted to go through that, and we will see you in class on Friday.